All right, in this worked example, we're taking a look at a circuit that has internal resistance. Previously, we'd worked with some examples where the internal resistance was negligible or we could ignore it, but that's not the case here. So this symbol right here is like an internal resistor, and this is the value of the internal resistance. They actually mention that in the problem right here. So we use the letter lowercase r for that. If we're trying to calculate the current in a circuit, and we can identify that this is a series circuit. In other words, there is a single path or a single loop that the electrons are flowing through, then we could use a procedure to solve for the current, where probably the first thing we want to do is calculate the entire circuit resistance. Okay, like what's the total resistance in this circuit? So calculate the total circuit resistance. Calculate circuit resistance. And whatever language will help you remember that. The entire circuit, the total resistance in the entire circuit. And depending on what type of circuit it is it a parallel circuit, a series circuit, or like we talked about yesterday, a complex circuit that has both sort of, types, we might have to use both of those equations. For this one, it's a series circuit, and so that's sort of the easier one to deal with. So the circuit resistance for a series circuit is just the sum of all the resistors. And so we've got a resistor X, we've got a resistor Y, we've got another resistor X, and we've got an internal resistor. So think about it, that as the current I is driven through these external resistors, it's also driven through our EMF source. And that means we're going to lose some volts here. I mentioned a moment ago that as soon as you see this symbol, you should immediately go, oh, V terminal PD equals E, the EMF, which is given here. They again mention it by name, minus the current times lowercase r. Right, so like that equation goes with this symbol. Connect those two things in your mind. Calculate the circuit resistance. Once you know the circuit resistance, you know how much this circuit resists the flow of charge, right? And the rate of flow of charge is I, the current. So in order to show that the current is a certain value, we're going to use my buddy George Ohm's law. Use Ohm's law. And so if we're solving for current, then it's I equals V over R, where this R is the combined circuit resistance. Right? Remember, we can apply Ohm's law at different places in the circuit, but if we're calculating like what's the total charge, the total current coming out of the battery, so YouTube, that's not the dismissal bell. This is fourth period. It's the lunch period. So like you've got third lunch, and it's the worst because like we're so hungry, and that's why we make mistakes with our calculations. So yeah, ignore that bell. You're not dismissed, YouTube. We got to keep on working through it. Do you've got lunch bells like that on your campus? If so, leave it down in the comments below. While you're at it, don't forget to subscribe, like the video, and all that stuff. All right, who's got the actual value of the current in the circuit now? I'm asking YouTube, not you guys. Okay, you guys, who's got it? Yeah, call it out if you know it. 7692 amps, we'll say, and that is indeed about 2.8. So that's how you show it, right? Plug in the 9 volts. Now we've already dealt with the fact that there's internal resistance, right? We added it in to our circuit resistance over here. What did you get for the denominator here? Right, everybody should have calculated that to be 3.25 ohms, right? So the 0.15 plus 2.7 plus another 0.15. So there's 3 ohms of external resistance plus our 0.25 internal resistor, right? So you just sum the resistors in a series circuit. If here we're showing that the current is a certain value, and we know that to like, hey, go right to this equation when you're looking at a circuit like this, we can anticipate the next calculation. We know the EMF, we know the current, we know the internal resistance. What do you think we're going to solve for? Well, the only unknown, right? Like there can only be one unknown. So there's 1, 2, 3, 4 variables in this equation, and we're given 1, 2, 3 of them, right? So solve for the other one. So indeed, the next question, the wording of it is calculate the potential difference across the battery. the potential difference across the battery. So always remember voltage across, current through. So the potential difference across the battery is the terminal PD, right, which is V. And so this calculation, this is what we were talking about a moment ago, like the math isn't too bad here. 9 volts minus, now remember, this is a voltage too, right? We could rewrite this like V equals IR like that, right? So anytime it's I times R, that's a voltage. So these are the lost volts. I'll use the 2.7692 amps, but you could use 2.8 if you wanted to. The answer will basically agree. And so 9 volts minus these lost volts. I'm going to keep track of my lost volts. Okay, so remember, I times lowercase r is the lost volts. And if we just multiply those two numbers, how many volts are we losing here? 2.769. Well, actually, let's do it. 9 divided by 3.25 is 2.769230.769, right? So I got that whole number in my calculator. Okay? All the decimal points there. As far as my calculator will show it. Times a quarter, 0.25. So the product of this current and this internal resistance is equal to the lost volts, 0.6923 volts. So I have a 9-volt battery, but because I'm driving 2.8 amps through that EMF source, through that battery, I'm going to lose about 0.7 of a volt. And so the terminal PD, the potential difference across the battery, is going to be, 9 volts minus 0.6923 volts. So 8.3 volts would be the terminal PD. Even though it's a 9-volt battery, there's only 8.3 volts available at the terminal ends of the battery, okay, to power the external resistors, right? We are losing 0.7 of a volt thereabouts, okay, by driving that much current. And if we arrange these resistors a different way, like what if we put them all in parallel, right? Then we'd be actually drawing more current than this from the battery, right? Because we'd have more paths for the electrons to flow through, so less circuit resistance and higher current. Then we'd be losing even more volts, right? So the more current you drive through an EMF source, the more volts you're losing, because R is fixed. It's based on like how good is the battery sort of designed. But the more current you drive through it means we're going to vary the lost volts there too. And that's the dismissal bell. Yeah, we wish, right? Yeah, there's several more bells. All right, so we took care of that, calculating the potential difference across the battery. Oh, great, there's more. Like there always is. All right, if you needed any of that working for a moment or two longer, we'll just pause the video and rewind it and watch it at your leisure. That's why it's, it's up there on YouTube for you guys. All right, each resistor X connected in the circuit is made from a wire with a certain cross-sectional area, and the number of free electrons per unit volume is given there. That given information should jog your memory to an equation that we derived a few weeks ago, okay? So you say, okay, and if it didn't, then maybe calculate the average drift speed of the electrons would. So hopefully, you read that and you go, oh, that's the equation for current I equals NAVE. V is the velocity that it's talking about right here, the drift speed. So if we're calculating that, then we want to go V equals I over NA. We mentioned last week about, how many equations do you know, like for resistance? So how many do you know for current, right? I equals V over R, I equals NAVE. Lots of different equations, right, for current as well. Kirchhoff's first law, sum of the currents in equals the sum of the currents out, right? So different equations that contain them. All right, so we know that the current going through that is 2.7692 amps. The number density is the number of electrons per unit volume, and they give that here. So N is 8.5 times 10 to the 29. Now it's electrons per cubic meter. So I'm going to put the per cubic meter back up here in the numerator. Okay. Right, so it's the negative index here, right? Because it's per unit volume. So this is electrons if you want, like, okay, number of electrons per unit volume. Electrons just a number, right? So there's really no unit there. It's just a thing, an amount of electrons, right? Remember what E does, it charges them up, right? That's really where we get this, I is Q over T. And so we got to charge up our electrons with elementary charge here, E. But we're getting ahead of ourselves. All right, so the area is given in these units here, millimeters squared. Because the number density is in meters cubed, as it should be, right? The base units of volume there, we need to convert that into more sensible units for the calculation, so it's consistent. This goes back to midterm review. We mentioned, how do you deal with square or cubic units, right? We got to convert that twice or 3 times, depending on if it's squared or cubed, respectively. So I'm actually going to write this down here so I got a little bit more room to work with. So 2.5 millimeters squared. I always write it out like that the first few times that I do it to remind myself I got to cancel them both out. So I'm converting millimeters to meters twice. And there are 1,000 millimeters, 10 to the 3, 1,000 millimeters in a meter. So to convert square millimeters to square meters, you have to divide by not 1,000, but by 1,000,000, right? We're dividing by 1,000 and then 1,000 again, or 10 to the 6. If you're good looking at that conversion, or even just looking at this and you've done this enough in your life that you're like, I know how these go, that you can just say, well, that's going to be 2.5 times 10 to the negative 6, right? Because these exponents are in the denominator. 3 plus 3 is 6. It's negative. That's correct. That's evidenced by the bell, right? That's the sound of, oh, we just did something correct. And we'll hear it again and again throughout the lesson. And who knows E? I would say it's elementary, my dear students. I'll edit in after later. Because it's elementary charge. But what's the value? And what are the units? Coulombs of charge. So remember that charge Q is equal to current times time. The other week we had a quiz and it said define the coulomb. You guys were like, oh, define a unit. It's usually a quantity, no fair. But just go to the equation that can, that has the quantities and then think about it like that. Like, okay, so a coulomb of charge Q is equal to an amp of current times a second of time. So we know that this is 1.6 by 10 to the negative 19 coulombs as elementary charge. But are we cool if we plug in amp seconds for that? Is that cool with everybody? All right, so a majority of you said that's fine. Some of you are like, no way, leave it as a coulomb. Okay, fine, leave it as a coulomb. But I want to cancel these amps out. I want to cancel out 2 of those meters right down here to appreciate meters per second. Yep, it checks out, right? You get the units you expect when you substitute it incorrectly. All right, now go ahead and calculate there, YouTube. What do you get? Get out the calculators. You're watching on YouTube, maybe you got a calculator right there on your computer. You could queue up and, type it in. We were talking about this, earlier today, like, I hate making mistakes with my calculations. I'm such a careful calculator. I like to type this in and then divide by, open parentheses, type that all in, close parentheses, equals. And then divide by again, open parentheses, type that all in, close them, equals. Now, if you live a little bit dangerously out there, you're a risk taker, and you want to use like double parentheses, brackets or something like that, and calculate it in one fell swoop for efficiency's sake, go for it. You can do it. I mean, there's nothing wrong with that. But I just hate making a mistake. Like you're typing in this lengthy denominator and you forget the negative sign. It's like, I knew the physics and I pushed the wrong button and I got the completely wrong answer. It's such a shame, so I like to be careful in my calculations. I'm a careful calculator class. But, it takes me an extra, half a second. So, there's a time factor there too. The old time factor. All right, so what are you getting out there? Anybody got it? Well, you guys, this is all like dead time on my YouTube video right now. So like everybody's like changing the channel. They're like, oh, I'm losing viewers, right? They're clamoring for content. We got to keep it moving. What do you guys get? Call it out. this divided by this divided by this divided by this is slow, right? Don't just write slow, quantify how slow it is. What do you? So you got 8.14 by 10 to the negative 6. Already out there again now, or maybe you could round it 8.1, right? 2 significant digits. So remember, drift speed is pretty slow. You always want to check, is this reasonable? Is this a reasonable value? Because it can reveal a mistake. Like if you calculate a speed that is faster than the speed of light, it's not reasonable, class, right? Nothing's going faster than light. Now this is really slow, and we expect drift speeds to be slow. All right, the very last part of this paper asks us to consider what's going to happen if we decrease the diameter of that wire. So it says the two resistors X are replaced by two resistors Z made of the same material and length, but half the diameter. Describe and explain the difference between the average drift speed in Z and that in X. And so we had the equation I over NAE, which gives us the velocity. And now we're saying, well, if we half the diameter, what we're really changing is the cross-sectional area, right? We're not changing anything else there. And so we can say that the area we know is equal to pi r squared, but pi is just a constant. So we'll say, well, the area is really proportional to the radius squared. To half the diameter is to half the radius, right? Like you half the radius when you half the diameter. But you half squared the area. Okay, so we're decreasing the area by 1/2 squared. And so the area goes down by a factor of 4, right? It's a quarter as much, right? So if you have two circular cross sections, okay, for a wire, and this has a certain diameter d, and this one is half the diameter, you say, well, what's the area of this one compared to this one? It's 4 times less. It's a fourth. And so what we're changing here is that instead of A being A, now it's 1/4 A. And so if we're dividing by a smaller number, right, that's 4 times less, then our velocity is going to go up by that amount, right? We're dividing by a smaller number, so the electrons are faster. So describe, the velocity increases. You can even quantify it. You could say it's going to be 4 times faster because we're changing the diameter and therefore the cross section. So the area is proportional to radius squared, and velocity is proportional to 1 over the area. Right, so you kind of combine those ideas together and say, well, then the velocity goes as 1 over the radius squared, right? So by halving that, you're making this, you know, a fourth, or I'm sorry, 4 times faster, right? Dividing by a fourth rather. Not confusing at all.